Welcome back, everyone. So we continue with the second and the last talk for today, which is Eric Perlmutter, who will be talking about conformal methods in AdS Cft.
Thanks. Yes, so it's a pleasure to be here at this school/workshop. And so as an undergrad, I took some classes from Untitled, and Robert came to visit at some point and gave a quantum field theory lecture that I sat in on. So it's kind of fun to be lecturing to you. Probably won't go as well as the reverse, but let's see. So, good. So what does this title mean? I'm going to try to address two main questions in the context of AdS Cft over the course of the next 3 lectures, and the two questions are the following. First is, what is a holographic CFT? You guys read this size? Great. Second question is how to compute CFT correlation functions in AdS. And I'll take a wide lens on the subject. Many of you know something about AdS Cft, of course, and so I'm going to try to inspire people in the audience to work on this particular corner of what is a huge subject of holography, namely trying to classify the theories that have holographic duals and trying to understand what the properties of those holographic duals are, given some properties of the CFT. So I will try to take a modern approach to this subject, weaving in comments about the conformal bootstrap, which is another topic in CFT, and give it a sort of holographic spin. And that'll be a lot of the philosophical inspiration for everything I'm going to say. There's a lot of people in the audience who have worked on these subjects. Of course, I should note in particular Samir and Sufrat, who've both done some work on amplitudes in AdS. And so actually tomorrow's, Monday's first lecture will largely be reviewing many results that Samir and friends derived back when AdS Cft was first invented. So, what is the more detailed lecture plan? Something like the following. So, first, for the sake of completeness, I'll talk about some AdS Cft basics. I'll try not to belabor the point, but I just want to set some main points out there, and even if you have some basic familiarity with the subject, I think it'll be useful for what comes after it. Next, I will talk about the question of what is a holographic CFT, part 1. Then we'll focus on the CFT side of the second question, which is how to compute CFT correlators. After this, we'll revisit the question about what is a holographic CFT, part 2, with the eye toward moving into the bulk. We'll then talk about the computation of CFT correlators as AdS amplitudes. And after having done all of that, which I think is pretty interesting in its own right, we'll talk about some newer developments with which I was more directly involved, which will mainly focus on 2 things. The first is how to represent conformal blocks in anti-de Sitter space using geometry. So CFT conformal blocks in AdS. And the second is how to compute loop amplitudes in AdS corresponding to non-planar higher order corrections to CFT correlators in the 1/n expansion. So these two are based largely on papers. This one just came out a month ago, and this is from sometime last year. And the rest is mostly work I didn't do, but it's a great subject, and I think there's still many existential, ontological, open questions, and that's what this will largely be about. Okay, so, of course, please interrupt whenever with questions. So, AdS CFT basics. Having just gotten here yesterday, I'm not exactly sure what was talked about before, but again, just pardon me for being redundant, but it's important to set out some elementary aspects that are crucial for the rest. So if we consider AdS in d+1 space-time dimensions, space-time metric, it's not so important for what comes later, but when I talk about AdS CFT, it should be written once. So in the Poincare patch, the metric looks like this. These are the spatial coordinates of the boundary CFT. This is the radial coordinate. Notice it's conformally flat. And we can draw this in a picture like this. So spatial slices are planes, and there's some curvature as you move in the z direction into the bulk. The boundary is at z equals 0. And so in this slicing, space is the d-plane. You have written in Euclidean signature, but to make Lorentzian signature, just take one of these and make it time and flip the sign. We can also write it in, so this is the Poincare patch. If we write it in global coordinates, then I'm not going to write the metric because we really won't use it, but AdS should be viewed as a cylinder that is filled in. So this direction is time. This is the radial direction, just call it r. And the boundary CFT lives at the boundary of the cylinder. Time goes upward, and space is a sphere. So each of these cuts is a d-sphere, d-1 sphere rather, dth dimension being time. And so here, space is time across the sphere. In drawing pictures of the rest of the talk, I will mostly be working in Euclidean signature, and I won't really commit to either of these coordinate systems, but I'll draw AdS as a circle, as is common. And this, of course, is the sort of hyperbolic space with constant negative curvature. Good. So what is the basic statement of AdS CFT? It is that the gravitational path integral in AdS is equal to the partition function of the CFT. This is a bit loose and imprecise, so more precisely, in the bulk we have some bulk fields, let's just call them phi collectively. This can be some local excitation, or in general it can be some stringy field, some vertex operator. And this field is dual to some CFT operator O, say some local operator, or in more complicated cases something like a Wilson line, but just for the simplest case, let's talk about local operators O and bulk fields phi. Now, at the boundary of AdS, these bulk fields act as sources for the boundary operators O. So I can think of this boundary value of the bulk field as a source J, which couples to O by a term in the CFT action, which is roughly the form JO. And then, given this, I should view the CFT partition function as a function of sources for these local operators J, as equal to the AdS partition function viewed as a function of the boundary data for the bulk fields. So this is a generating function for a correlation function of the CFT, if you like, and it's equivalent to the path integral for AdS with all of its bulk fields, given the asymptotic AdS boundary conditions that we impose. Okay. Good. So let me do some erasing. Okay. So for the rest of the lectures, I'll talk about the dynamics of local CFT operators. So forgetting things like Wilson lines or entanglement entropy, just local operators. So let's understand how to characterize local operators in a CFT. Well, what is a CFT? So the C here stands for conformal, of course, and that means that the theory has an SOD, comma 2, global conformal symmetry. This is generated by momentum operators, special conformal generators, rotations and boosts, and a dilatation operator. So this here is like a raising operator. The Hermitian conjugate of that, K, is a lowering operator. These rotations are just the SOD subgroup of SOD, comma 2. And this here is the dilatation operator. Which rescales distances while keeping angles fixed. So altogether these form SOD, comma 2. One especially relevant feature of this algebra generated by these generators is that the SOD generators and the dilatation operator commute. And so what this means is that all local operators can be labeled by their charges under each of these generators. In particular, they can be labeled by a dimension delta, so by some operator OI, and it has some scaling dimension delta under dilatations and some set of spins J sub I under the SOD rotations. And so this you should think of as being the quantum number associated to the SO2, and these I should think of as being associated to the quantum numbers of the SOD, this being the maximal compact subgroup of this. So these belong to some operator O sub I. Okay, good. Mostly I'll talk about primary operators. What is a primary operator? A primary operator is one that commutes with K. So if I act with the operator at the origin, this commutes with K. Equivalently, if I make the state O, which is generated by acting with O at the origin in the vacuum, then K annihilates this state. Having constructed a primary, we can then flesh out the irreducible representation of SOD, comma 2 by acting with the raising operators P. These are like derivatives. In fact, they are derivatives. They generate translations. And so there is an entire infinite set of operators which are related to O by the action of the momentum generators.
Can I ask a question? Sure. Just on two-dimensional conformal theory. So this nice relation that the state O is created from the vacuum at 0, there is no divergence in higher dimension than 2.
Divergence.
Yes. This is a field operator which is normally operator distribution. In 2 dimensions this is correct. You can show that if you take Z to 0, that you obtain the normalized state. But in high dimension then I don't see you have some operator state correspondence or whatever which would guarantee that.
Yes, so the state operator correspondence works when you quantize the theory on the sphere times R.
Whatever
And
dimension.
in this case, when I say O acting at the origin, what I mean is, right, so indeed, so
If time goes to minus infinity.
yes,
I see.
time goes to plus or minus infinity. Yeah. And this is valid for all D. Yeah, thanks for asking. Good. So the conformal family of O includes an infinite set of operators. So let me write this in terms of the states. I just like it better that way. We can organize it like this. We'll see why in a second, and then again in lecture 3. So we can act with P of O multiple p's. And then we can also act with p squareds by contracting the indices. Right? So the reason I'm organizing it this way will become clear. And what do all these columns have in common? So each row has in common that it has the same number of p squareds. Each column has in common that the operators have the same twist. So twist is just something that we made up, defined as the dimension minus the spin. Here I have in mind operators that are, say, symmetric traceless tensors, so there's just one spin quantum number, which I'll call L. And the dimension minus the spin is the twist. And so you see that when I add a p, I increase the dimension by 1, but if the index is open, I increase the spin by 1, so the twist remains the same. And if I add a p squared, then the twist increases by 2. Okay, so these operators in this row have twist of O. These operators in this row have the twist of O plus 2. These have the twist of O plus 4, and so on. Okay.
To subtract the trace from the PU or just leave it as PU?
Oh, well, I mean, this is some level 2 descendant, but I can start subtracting traces, but I don't need to.
So, I mean, it may not be the useful representation the way if you don't subtract the traces.
Well, so, sure. So the point is that all of these possible actions altogether, suitably organized, generate the full representation. Yeah, thanks. Good. That kind of thing tends to be more important, it seems, when you're trying to make a primary state, for example. You know, say if you have some double trace operators, you want to subtract out the traces when you act with k so that the thing's annihilated. But here it's more of a formality. Okay, so we established roughly what conformal families look like, and we showed that operators are labeled by their spins and by their scaling dimensions. And the central thing about CFTs is that they admit an operator product expansion. In other words, operators interact. Okay. So if I have an operator O sub I, then I can generate an operator algebra by taking the product of two operators suitably defined, and thinking of this as a sum over some other operators in the theory, generally sum over all the operators in the theory, weighted by some structure constants, which you should think of as analogous to the structure constants of some Lie algebra. In 2 dimensions, this can be completely formally established. They literally are the structure constants of some vertex operator algebra. In higher dimensions, the analogy is just that. Nevertheless, these constants here are an essential ingredient of any CFT, and they parameterize the difference between one theory and another. Okay. So these are the OPE coefficients, and this notion of taking products of operators and replacing them by sums over single operators is called the OPE, the operator product expansion. Generally, this is valid to do when, if you have some spatial region, there's an operator OI, an operator OJ. You want to think of bringing the two close to each other, and you're allowed to do this as long as there's nothing else in between them, roughly speaking. Good. So, an important fact, and the whole reason I was going through these foundations, is that a CFT is fully specified by its OPE data, namely the spectrum of dimensions and spins, and the OPE coefficients, up to non-local effects. So, what constitutes a CFT? Well, perturbatively, or rather in terms of the local operators, the answer is a list. It's a list of data, so some operator dimensions and their spins, and the OP coefficients amongst all of them. That, in the abstract sense, defines for you a conformal field theory. And there can also be non-local operators, different loops and lines of various constructions, but modulo that, this essentially defines what a CFT is made of. In particular, all correlation functions of local operators can be determined in terms of these data. So, let's look at a 2-point function of operator OI, OJ. I'll be more precise about coordinate dependence and actual equations soon, but schematically, we can draw this as a kind of propagator, if you like, between two operators I and j. A 3-point function will be represented by some trivalent vertex, and this is just parameterized by a single constant,Cijk, which would appear in the OP of OI and OJ in front of OK. Things get more interesting when you look at 4 and higher point functions. And that'll really be the subject of what comes later. After all, so far up to here we just talked about 2 and 3-point functions, namely dimensions and OP coefficients, so what about 4-point functions? And so we can draw this by putting these ingredients together. Like so. The external operators are I, J, K, and L. And we can have some operator running in between, some operator M. And each of these vertices comes with an OP coefficient, and in other words, a 3-point vertex. And so on at all higher points.
So, a very nice question. Is it possible to find CFT with a 4-point function? Sorry, with a 4-point vertex?
No. That would, so the existence of the operator product expansion means that everything can always be reduced down to 3 points. I think that's one way to say it. So it's different from computing some amplitude where you have some quartic vertex. The statement would be that actually that can be reduced into sums of 3-point vertices squared. For example, said another way, given this, you can take this object and perform the OPE on 2 pairs. Nothing stops you from doing that, and then that answers your question.
I mean, there could have been an additional term that depends on all 4 simultaneously, but yeah. I guess what he's saying is that it's not compatible with the conformal symmetry. I mean, the conformal symmetry fixes to a certain extent how these operators can depend on the insertion points, and as a consequence, I think you can't add an independent 4-point vertex.
It's not consistent with locality.
Yeah, that's
even in non-conformal. I mean, I don't know how well the OPE converges in non-conformal field theories, but even then, you would expect that everything. You can always write the product of 2 operators in terms of single operaters. So there shouldn't be an independent 4-point term and an equivalent.
But I mean, Young-Mills, there are 4-point.
They're independent 4-point vertices. But that 4-point vertex, if you include double trace operators, can be reduced to a product of. So this is not in terms of the fundamental fields, right? This is all operators in the theory. So the Lagrangian might have an independent 4-point vertex. There'll still be an OPE which would say product of 2 gluon fields goes to a double trace operator of gluons.
True. I mean, if you add in more and more fields, then obviously you cannot do it.
Right. So
it depends on your choice of fields whether you will have independent 4-point vertices.
But do you know any theory in 4 dimensions which would have independent 4 vertex?
I mean, in a
on a
sense,
certain level, Young-Mills, right?
But this is perturbative stuff. This is
Yeah, but I mean,
it's nothing
as
to
a
do with
vertex
this
in your
picture.
Lagrangian, it's a 4-point vertex, right?
But this has nothing to do with that, isn't it?
Right, it's a field theory where you have
It's
an
an
open
operator
vertex.
product expansion. By definition, you can reduce it to 3 vertices.
I mean,
But I think that requires you to add in additional fields.
additional operators,
Well,
right?
this
So
is
those
operator,
OIs
yeah.
includes also in a phi to the fourth here, you would have phi and a phi squared would be one of the other operators that would run.
Right.
So even at the fundamental vertex is 4 points, this would still look 3 points.
A sort of slippery answer to your question is that so there's a 4D theory that has quartic vertices and it just lives in AdS 5, but it's for a different set of fields.
What did you say?
So the AdS CFT correspondence tells you that there's a sense in which I can describe a CFT in terms of something with 4 and higher point vertices. It lives in AdS, it's the theory that's dual to that CFT, and if I want to think of the quartic vertices I might have in my bulk action as answering this question affirmatively, I'm free to. But of course it's a different theory, it lives in a different space-time, and the constituents are different. But it makes manifest that you're talking about gauge-invariant operators. So
as far as if it is a quantum field theory, then you
Yeah,
have
no,
also
I agree.
operator product function.
yes, I stick to that. But I mean, this is maybe a different way to answer this question. That applies at least for certain classes of theories that have AdS duals, although I think that all theories do on some level. Is there a question? Good. Okay. Right, so now on to the holographic parts. That's good timing. Okay. So of course, the AdS CFT correspondence was first quote-unquote derived in the context of string and M theory, but by now we think of this as a general concept independent of any string or M theory construction. And in a sense, this talks about working backwards from the CFT side into the bulk before you even know what is living in the bulk, whether it's a string theory or not. Nevertheless, the best studied examples of the correspondence involve theories of strings or branes in the bulk. And because I'll make reference to a handful of these theories sporadically, let me just sort of write down the best studied examples of AdS CFT. So this will be pictures. So in 2 CFT dimensions, there's the CFT that lives on the intersection of D1 and D5 branes in type 2B string theory. So again, if this is not your speed, that's okay. So here I have some stack of D5 branes. I have a lot of them, a large n number of them. And sitting embedded inside these D5 branes is a set of D1 branes. These are objects that have 1 space dimension, these have 5 space dimensions in their world volume, and living on this 1 + 1 dimensional intersection is a CFT. So that CFT lives here. This case is slightly less straightforward than the other 3 paradigmatic cases, which just involve stacks of branes without any intersections. So a 3D CFT that we often talk about is native from stacking M2 branes in M theory. This is the ABJM theory. In 4D, of course, you have the mother of all AdS CFT examples, which is the n = 4 Super-Yang-Mills theory, which lives on a large n number of D3 branes. And we've got a little room down here for 6 dimensions, where we have a similar example now just with a stack of M5 branes. And this theory we refer to as simply the 2, 0 theory. This stands for the level of supersymmetry it has, and we call it this because we don't really know much else about it. So we just call it by its amount of supersymmetry. Actually, in fairness, it's not any worse than just calling this by the names of the people who invented it. So if you look at this, you don't really know much about the actual theory. But these are the 4 cases where we understand a bit what's going on from the bulk and largely from the boundary, especially in this case, to some extent in this case, to an even lesser extent here, and much less here. But I'll talk about improvements using the conformal bootstrap as we go along. Note that all of these actually have maximal supersymmetry. These are supersymmetric and conformal stacks of branes. And that's part of the reason that they're the best understood. We wish we could get away from that, but it's hard, so we're trying. So that's sort of a lightning review of some traditional AdS CFT constructions that set the stage for more generic investigations that involve increasingly less symmetry. What time is it?
You have about half an hour.
Great, thanks. Okay, so is this pace good for? Okay, good. All right, so if we think about the class of CFTs that might have AdS duals, we might ask, what are those that do? The strong form of the correspondence that has really been around since its inception is that every CFT has an AdS dual. Now when I say AdS dual, there are many possible theories of gravity, of quantum gravity you can have that live in anti-de Sitter space. And the question is, what properties of the CFT map to what properties of that theory in the bulk? Most CFTs probably are not so nice as those I wrote over there, which is to say that if they have an AdS dual, it's very strongly curved, or it has finite length strings, or branes, or other stuff that is tough to handle analytically. But if we just go with this strong form for a moment, then we can imagine a mapping between the space of CFTs and the space of theories of AdS quantum gravity. So let's draw this in the spirit of the Bootstrap. So we have two spaces. On the one hand, the space of consistent, unitary, causal, ... CFTs. And on the other hand, theories of AdS quantum gravity. And we'd like to know the map between these spaces. Moreover, there are certain theories that are more well-behaved and more tractable. So for example, you can imagine some subset of all CFTs that live in a family that emits a large n limit. What do these correspond to? Well, there's some corresponding region over here where the theory of gravity in the bulk is weakly coupled. Which is to say, the Newton's constant is small. And there's some relation between Newton's constant and n that is of inverse proportion. We can then specialize further. Let's just not have just large n, let's have other conditions on the spectrum, say. So we have some region here where the theory not just has large n, but actually has a sparse spectrum of light local operators. So what would this look like? This would look like some classical theory of gravity in AdS that is not just weakly coupled or classical, but looks something like Einstein gravity. Coupled to some order 1 amount of matter. So we have not been terribly precise about what exactly this region means or what sparse means. For now, it just means what you think it would mean, not that many. But if I imagine theories that have not that many light operators, we know experimentally, for example, by studying those examples, that in these cases, the bulk theory has gravitational dynamics that are described by Einstein gravity as opposed to something with higher derivative couplings like Gauss-Bonnet or something even worse. The motivation for a lot of this talk will be to understand exactly what this means, and we'll come back to that at the start of the next lecture. You can also imagine another region of this space which is not as nice in the bulk, so maybe it just has large n, but instead of being a sparse theory, let's get this checkerboard. We could have some theory that, say, is weakly coupled, which generically means that the spectrum of light operators is not sparse, it's actually highly populated, because operators don't acquire large anomalous dimensions and decouple and become heavy. This would be dual in the bulk to something which is classical, but for example, stringy, or, well, I don't think this is really a word that people use, but brainy. So unlike Einstein gravity, where we just have some local operators and there's no strings around, we can now add some strings, and we have a finite string length. And in particular, the AdS radius will be of order the string length examples like this. So making this more precise will be something we'll do later. But first, I will find it convenient to talk about more aspects of what it is we'll use in CFT to understand this relationship. Okay. But just to recapitulate, the question is, what is a holographic CFT? One way to phrase that is to understand, first, what are these spaces and what is the mapping between them? And this is sort of a bootstrap problem for AdS CFT. That's how I think about this. The general bootstrap problem, and if you're not familiar with the bootstrap, I'll define it by the end of the lecture, is to just classify this space in complete generality. If we then impose further conditions like log n, a sparse spectrum, and so on, now we're talking about aspects of theories that look like theories we'd like to make in the bulk. And that's the sort of holographic version. So this is the philosophy. But it's a physics school, so philosophy only takes us so far. And we should write some equations. So that's what the rest of the lecture is about. If I could put philosophy into equations, that'd be very interesting, but instead I'll talk about something else. So let me make a sharper version of this question that I just asked. The sharper version is something like the following. So what do the spectrum of operator dimensions and OP coefficients, that is to say, the CFT OPE data, what do these look like in holographic CFT? We can understand this by studying correlation functions in AdS and backwards engineering what properties they have to have, or just studying CFT observables and sort of inferring in the opposite direction. And the key tool we use in this talk is to study correlation functions. Okay. So there are, of course, many aspects to this question, or rather this question of classifying holographic CFTs. But when we talk about the OPE data, well, this is all accessible by studying correlators with local operators, so that's what we're going to do. You could study many other things, Wilson lines, thermal states, entanglement entropy, but to access this data most directly, correlators are the way to go. Incidentally, they're one of the most basic observables in CFTs in general, so it's a good thing to know about, and was one of the first things to be studied in the context of AdS CFT. Nevertheless, we're still a long way from really understanding in full completeness how to study correlators holographically in a nice way. And that's what tomorrow and the third lecture will be about. So, as we discussed before, 2- and 3-point functions are too simple to really access the full spectrum, but 4-point functions are not. So now we're going to talk about computing 4-point functions in CFT, and next lecture we'll talk about how to do that in AdS. So, one side point is that even in supersymmetric theories, 4-point functions can access unprotected information. So if I look at a BPS operator, then its 2-point function is determined by its dimension. Its 3-point function is determined by itself, just as a number. And if this is a BPS operator, then the dimension is protected. And in many situations, like n equals 4 super Yang-Mills, the 3-point function is also protected. By protected, I mean if there's a coupling constant, like there is in n equals 4 super Yang-Mills, then this object does not vary as a function of that coupling constant. So in particular, as in that case, if there's a region in the moduli space where there is a free theory, this can be computed in the free theory, and that gives you the answer even at strong coupling where gravity is relevant. But if you look at a 4-point function, then this is not protected. even if O is BPS, it's not protected. And the reason is that this gets decomposed, right? This gets decomposed into sums of 3-point functions, and unprotected operators can appear in the middle. So you have 3-point functions of 2 protected and 1 unprotected operator. Those in general are not protected, and so this gives you access to information that sees the emergence of a bulk spacetime when there is one. Okay, good. So that was a side comment about supersymmetry. Now we'll talk about some pure CFT aspects of 4-point functions, and that'll take us to the end. As I erase, let me make a sort of side remark, which is that even in cases where things like 3-point functions are determined in principle by supersymmetry, it's often very hard to compute them. So there are many challenges even in the supersymmetric case, and I am not as qualified to speak about this as other people in the audience. Suffice it only to say that, for example, in the IBJM theory that I talked about before, this 3-dimensional maximally supersymmetric theory, there are many 3-point functions that are protected, but we actually don't know their values. Okay, so some of these have been determined recently by using supersymmetric localization. Many of them are not known. So even when we add all this supersymmetry, life can still be hard. Okay. But now we're going to remove it and just talk about general aspects of 4-point functions. Okay. So just to set the stage for completeness, let's talk about 2- and 3-point functions, as I promised I would do. So I have a 2-point function of 2 operators, O1 and O2, at 2 different positions, x1 and x2. Then they can be normalized such that this is equal to the inverse power of the difference of their distances, which I'll write as x1, 2. And this is only non-zero if delta 1 equals delta 2, namely if they're the same operator, if they're primaries. So 2-point functions are diagonal. One can always find a basis where this is true, and the dimensions must be the same to get a non-zero result. And conformal symmetry just fixes the answer to be very simple. It's just an inverse power of the difference in the distances between the 2. Okay. Now if we look at 3-point functions, this is equal to the OP coefficient we talked about before over some position-dependent thing. Right? So it's proportional just to this constant. We want to do better. So now let's talk about 4-point functions. We're going to consider 4 different operators, O1 at x1, up to O4 at x4. And in general, this can be written in the following form. So let me just write this. In case I think I said this but didn't write it, xij is defined as the difference between xi and xj. So likewise with delta ij, anything with an ij type subscript. There's some power law stuff that is there, and it's kind of boring but important. So it's a bunch of power laws where the exponents depend on the dimensions. Here are their differences, here are their sums. And then there's some function, which I'll call A, of u and v, which are defined as the conformally invariant cross ratios formed out of these positions. So u is defined like so, and v is similarly defined. Great. So all the non-trivial information about a given 4-point function lies in this function A. Right? A, so far, can be anything. It just depends on these conformally invariant combinations of coordinates, and that's where the theory dependence lies. So, dynamics lies in A. Okay. Good. So what are we going to do here? We're going to decompose this into sums of 3-point functions squared, as we discussed before, and that will show us a more efficient way to compute this. So now I'm going to devolve back into dropping coordinate labels just for the moment. So we look at a 4-point function of identical operators O. We want to write it as the sum over other operators O prime that live in my CFT Hilbert space. And schematically, we're just inserting a complete set of states. Think of this as an insertion of a complete set of states in between the two pairs of operators. And this is our answer. Okay. Each of these is a 3-point function, and there's some coordinate dependence that comes with this. The whole sum here defines this function A, and what actually appears here, and with what value, is where all the meat is at. So here O prime runs over all the operators, primaries, descendants, everything. There's a better way to organize this. Instead, why don't we write this over sums of primaries only, which I'll call O sub P, which again live in my CFT Hilbert space. Let's draw this like so. So I have OP propagating in the middle. Now, obviously the whole result can't be written just in terms of primaries. So now we're going to take this object here, not just to represent the exchange of a single operator OP, but the exchange of its entire conformal family, so OP and all of its conformal descendants that we talked about before. That object is called a conformal block. And this is the contribution of OP and all of its descendants. The point of doing this is that this object here is just determined by conformal symmetry, whereas the dynamical information, so to speak, is just sitting at the vertices. These OP coefficients, C, O, O, O sub P. The rest is just redundant, and we can just fix it once and for all by deriving this conformal block and expanding this object in those blocks. So we've dramatically reduced the amount of information we actually extract from this because a lot of it is just related by symmetry.
It's a bit strange in higher dimension. In 2 dimensions, the conformal symmetry is very large, so you have multiplicity. In higher dimension, that the conformal symmetry would fix completely the form of the conformal block. This is true.
It does, but there's the same statement is true in 2 dimensions if you just look at the global conformal symmetry, the SL2R subalgebra of Virasoro. Then that is exactly analogous to what I'm defining here.
Yes.
And that's the end of it, yeah. So in the same way that that hypergeometric function is just fixed by the SL2R symmetry, here there's some function, which I'll describe more in detail, that is fixed by the SOD, 2. Great. Yeah. So in terms of the less schematic equations over there, the statement is that this A can be written as a sum over primary operators, C1, 2, B, C3, 4, D, times the conformal block, which I'll call capital G, with the subscript delta P to stand for the quantum numbers of the exchange primary, which itself is a function of the coordinates U and B. This is the block, and this is what we'll spend some time talking about now. All the theory dependence lies in what the sum is over and what these numbers are.
Okay. G depends on the dimensions of external operators.
Yes, I'll write some formulas soon. So we're going to spend 10 minutes talking about conformal blocks and perhaps defining the conformal bootstrap. So what do we know about these blocks? Quite a bit, actually. So they are known in all space-time dimensions, so for all d, in various forms. So there are series representations, integral representations, there are solutions to known differential equations. What else is there to say? They're known in closed form in even space-time dimensions, including 2. And there are also recursion relations that approximate them to very good accuracy just by keeping some number of terms in the series. So here I'm just going to talk about 2 of those representations just to show you what these things look like. And the last lecture I'll talk about the other 2. So first, here's the series. So G sub delta comma L, and V, can be written as a series in powers of U and 1 minus V. So n and n run from 0 to infinity. Some constant C sub mn, U to the m, 1 minus V to the n. And these C mn's are equal to the following thing, to answer your question. There's a bunch of Pockhammer symbols. These expressions have some nice symmetry to them. And are relatively compact. So let's stare at this a little bit. So delta 1, 2 is delta 1 minus delta 2, right? So one thing to notice is that the block only depends on differences of the external dimensions pairwise. So for example, if you have a block for external identical operators, as we often look at, the block actually does not depend on the external dimensions at all. The space-time dimension appears only here, in the denominator. Notice that when d is even, d over 2 is an integer, and that's responsible for some of the simplifications that occur in even dimensions. Namely that actually this can be resummed, both sums can be performed, to get some closed form expression, which I'll write soon.
There's no L dependence.
Good. Where's the L dependence? Yeah, sorry. So here I think I just wrote the scalar block. Excuse me. But there's some simple modification for L dependence, but I don't want to screw it up by ad hocing it.
So it's for like all external operators are scalar and the internal thing is also scalar.
Yes. Yes, thank you for getting me to clarify. So here the external operators are scalars, internal operators are scalar as well. So you might ask, what is known about when external blocks have spin? And the answer is that's a much more recent investigation, but actually by now we know quite a bit. In 3 dimensions, we know all of the blocks when the external operators have spin, because the only spinning representations are symmetric traceless tensors. Once you go to 4 dimensions, you can have various representations of the Lorentz group. And right, that's because here the rotation group is SO4, so now there's 2 spin quantum numbers. And we know quite a bit about that case, but it's just a little nastier because there's more complications. But this is understanding spinning conformal blocks, as they're called, is an area that continues to be active. Okay, good. So in even dimensions, and on a closed form,
Including spinors is also okay, means there's no problem with that.
that's also on the under the category of more recent investigations. Yeah. So for example, in 3 space-time dimensions, we now know all the blocks for external spinners of arbitrary spin, I think. I'm not sure about arbitrary dimension. In fact, I'm pretty sure that in arbitrary dimension we don't know the answer. Closed form. Yeah.
you take the larger conformal blocks you get for 2D conformal symmetry, do you still have the property that everything depends only on differences of dimensions in the conformal?
No.
This is just for the small algebra.
Yes.
I don't
Yeah, so talking about Virasoro blocks would be the subject of its own lecture, which would be really interesting. I decided to not say much about that, but it's come up twice, so I'll make some remark, which is that in 2 dimensions, you don't just have the SO2, 2 conformal symmetry. That gets extended to a local conformal symmetry, which is infinite dimensional, which is then the Virasoro algebra. There are 2 copies, one on the left, one on the right. And so associated to that, we can define conformal blocks if we want to. The Virasoro conformal blocks are not known as well as we'd like. We know recursion relations for them, and in various large central charge limits, we know quite a bit about them. But for generic central charge and generic internal and external operator dimensions, we don't know a nice, tidy expression for the Virasoro blocks. This is a blessing and a curse. It's a blessing because the structure of quantum gravity in AdS3 is very closely related to the Virasoro symmetry of 2D CFTs. So even more than in higher dimensions, when you look at quantum gravity in AdS3, a lot of the dynamics of the bulk are fixed by symmetry. However, it's a symmetry that we don't understand as well as we'd like. So the Virasoro algebra itself is very easy to write down in 2 lines, but understanding its consequences will probably take many more years, and is closely related to the complexities of studying quantum gravity in AdS3. When we look at classical limits, we can understand things quite a bit better. But that's definitely, it's interesting on big subject. Okay. So let's just write the expression for 2 dimensions. That's especially nice. It just turns out to be a product of hypergeometric functions. L. Let me introduce a new notation, which is common for 2 dimensions. I can rewrite my cross ratio U as Z times Z bar, and write V as 1 minus Z minus Z bar. I also see these often in higher dimensions, so this is useful to know. But this is especially useful in 2 dimensions where Z and Z bar are just complex coordinates for the 2-dimensional plane. And we write the block as a function of Z and Z bar. Then in 2 dimensions, it's just the following. It's this squared, where H is defined in terms of delta and L, like so. Again, this is some common 2-dimensional notation. But if I define delta as H plus H bar, and the spin as mod H minus H bar, that defines H and H bar. And again, you should think of H as the scaling dimension associated to the left-moving half of the global conformal symmetry, and H bar is associated to the scaling dimension of the right-moving global half of the conformal symmetry. Okay. So this is very nice. In 4 dimensions, there's kind of a similar expression. It's a sum of products of hypergeometric functions. So it's a sum of 2 terms, which is a product of 2. Each one is a product of 2 2f1s. And in 6 dimensions, there's something vaguely similar. But in all even dimensions, it seems that it can always be written as sums of products of 2f1 hypergeometric functions, which, all told, is a pretty nice class of functions to be dealing with.
This 2-dimensional expression, again, there is no dependence on external state?
This must be.
So here I'm talking about the global block. So I have specialized, sorry, here I've specialized to the case where they're pairwise identical. Yeah, excuse me. I was not clear about that. Yeah. If I don't, then these become H plus delta 1, 2. That becomes H plus delta 3, 4. Something plus H 1, 2.
Probably missing something important that in 2 dimensions, so Virasoro stuff is not known. But if you use just SO2 stuff, it is known.
Yes.
So you cannot somehow. You use less information and you have a complete answer.
Well, it's a much smaller problem, so it's not immediately
The
clear which one
problem
wins.
is
But
that at the end of the day, you have a 4-point function which you want to calculate. And you say that all dependence of 4-point function is in UV dependence plus the structure constant C. And UV dependence you know explicitly. So
Yes.
It boils down to structure constant. And if you use more information, which is a VSO, you cannot do that because you don't know conformal block explicitly. It looks puzzling.
You should think of it as inherent in the difficulty of Virasoro representation theory. It just so happens that SOD(2) is tractable, but Virasoro is not.
Essentially,
So
you say that you can obtain conformal block of Virasoro somehow from this block.
Well, as an infinite sum over global blocks,
Over global
absolutely. I mean, that's done. That's a done deal. The question, but it's analogous to the difference between using conformal blocks and not using conformal blocks. If you don't use them, then you just consider independent operators propagating in the intermediate channel, descendants and primaries. That's fine. Each one is just some power, and you're not doing anything wrong, but you're just trying to save yourself some time, because many of these terms are related to each other by the symmetry. And if you can manage to sum them up, then you'll never have to think about descendants ever again. Likewise, if you want to go from global to Virasoro, if you can manage to sum up all of the Virasoro, all of the global exchanges involving increasing numbers of stress tensors, then that's great. But we can't, but there's no conceptual paradox. It's just.
But what it is good for to know explicitly those conformal block in your stuff, AdS, Cft. I would say, yeah. What is it good for?
I'll hopefully answer your question by the end of Monday. Yeah. So the short answer, I mean, not to leave you hanging, this is a day in between, is that it turns out that conformal blocks have a nice geometric representation in AdS. This is just interesting if you're interested in holography, first of all. But second of all, they become very useful when you want to compute full 4-point functions by summing up Witten diagrams in the bulk. Because they give you an object that manifestly emerges when you try to decompose Witten diagrams into conformal blocks. And once you recognize the holographic dual of a conformal block, then the 4-point function calculations become much, in a sense, much easier and more natural.
And in the gravity side, there is an independent calculation which would match the conformal block.
So this is something you can prove. We wrote down a geometric expression. We can compute it exactly and show that it matches known expressions for the conformal blocks. So in a sense, it's not a dynamical statement about holography. It's something that's fixed by representation theory. And AdS has the same symmetries as a CFT, so you might have imagined this was possible,
Yes,
and so it is possible. Okay, let me wrap up in a couple of minutes. So there are some other representations of these blocks that will be useful. I've really just written a series and given you one example. Namely, there's an integral representation, and there's solutions to a Casimir differential equation for the conformal group. Both of these will make appearances later, so that's okay that we don't have time for that now. And let me close with the following property, not of conformal blocks, but of correlation functions themselves. So far we've just written the function like that as a sum over blocks. We've just used symmetry to, in a sense, simplify the problem. That's fine. But there's a constraint that this function A has to obey, which is critical, and that is the constraint of crossing symmetry. Which is the following constraint on A. If we imagine a 4-point function of identical operators of dimension delta, just to make things a little simple, and A carries no indices for external operators, and it has to obey this equation. So v to the delta times A of u and v is equal to the same function with u and v switched. So where does this come from? Well, this comes from the associativity of the operator product expansion. That is to say, when I expand this in blocks, I can choose to perform the OPE on any pair of operators, for example, this one. But I can also choose to perform the OPE like this, or like this. Now it's getting a little weak in the lines. So there are 3 different ways to pair up the operators. And associated with each way is a different, what we'd call a different channel for the 4-point function. And the statement of crossing symmetry is that the result has to be invariant under which choice you make. So here I've written an equality between 2 of these choices, and there's a 3rd channel where there's some likewise equation that appears as well.
But on the gravity outside, what is the principle which would explain this?
Oh, that's an interesting thing about AdS Cft. So in AdS Cft, when you compute correlators, in the bulk, the crossing symmetry is completely manifest because you're just instructed to explicitly sum up different channels. Whereas in CFT, this is highly non-trivial. So it's kind of a magical fact about holography that for theories that admit some AdS dual, when you compute their correlation functions holographically, crossing symmetry is not a constraint. It's an input. But in CFT, this is highly non-trivial. So this is non-trivial because the conformal blocks themselves are not invariant under crossing.
But I mean, in CFT, it's also automatic if the theory is consistent.
Yes.
You're just saying when you try to put it together out of your Lego building blocks, it's not obvious that any way of putting them together will work.
Yes, yeah, thank you for clarifying that. I'm doing this in the space of CFTs before I know what the OP coefficients and dimensions are. This constraint must be satisfied, and if we turn this around, then this gives us a way to constrain the OP data itself, and that is the program with the conformal bootstrap.
You said that it's a consequence of associativity of operating product expansion from stop.
Yes, but maybe the question is then, what are the possible operator product algebras? And you use this to try to constrain them. That's the approach.
I missed the thing. Didn't you just say that conformal blocks are equal to these Witten diagrams? Are the Witten diagrams by themselves crossing symmetric?
No, the diagrams are not crossing symmetric, but
The
you
sum of
add
various
the
diagrams.
cross versions to each other. So it's like summing over images.
Yes.
Yeah. Good. So this is the solving this equation is the goal of the conformal bootstrap. When one works abstractly in the space of CFTs without specifying the actual OPE data. A key constraint that allows you to actually get somewhere is that these OPE coefficients should be real in a unitary CFT. So,Cijk squared should be non-negative. And this allows you, when studying this equation, to try to perform the following operation. So the goal is as follows.
This looks very true.
But I haven't told you anything about
Well, this allows.
Oh, this looks true. Oh, it is true in unitary theories, but the point is that if you do this equation, maybe it's a little more natural to move this to the right-hand side and think of something equaling 0. Now, the something is comprised of units that are that sort of want to be positive. So the goal is to try to make some assumptions about the spectrum and the OP coefficients such that the thing on the left-hand side has all positive terms when you write it as a sum over blocks. Then it's now possible to equal 0, and you have a contradiction. And then you've ruled out a certain part of your parameter space. So the output of the conformal bootstrap is ruling out possible spectra and OP coefficients. And I was trying to get my laptop to work so I can show kind of a fun plot or sort of movie of some recent sort of bootstrap result. This is not related to holography, but it's important for the sort of modern perspective I'm trying to advocate. So a common type of plot you see is that you have some operator O, which has some dimension delta, and there's some other operator O prime. And we assume that these are, say, the two lowest lying operators in our theory. And then we want to ask, say, given some assumptions about the global symmetries of our model, what is the possible space that these dimensions are allowed to occupy? And it turns out that actually this equation is quite powerful. And for example, I mean, at this point, somewhat famously, in the case of the 3D icing model, you can actually constrain the space quite a bit. And so there are plots that you have where there's, say, some little island, which is allowed, and everything else is not allowed. This is a bit of a caricature, but the point is that upon making some mild assumptions and imposing that equation, you find that there have to exist some field theories that obey your, or there may exist some field theories that obey your assumptions that live in here. And it turns out that the assumptions are often based on field theories we know, and there's this sort of game of trying to show that the field theories we know are in some sense inevitable or saturate the bootstrap bounds. So for example, in the case of the 3D icing model, this island has become smaller and smaller as they've gotten better and better. So now there's some sort of tiny island, and now I'm just drawing a sketch, and this is basically meaningless, but there's some parameter space which has some tiny island which is allowed, and actually it just turns out that from other analyses, like Monte Carlo simulations, we think the 3D icing model sits somewhere in that island. So this speaks to the impressive power of the Bootstrap to isolate the parameter space of CFTs. And so next time we'll talk about how to compute correlators in holography and applying the Bootstrap philosophy and on some level literally applying the Bootstrap to large N CFTs and asking what this tells us about the theory in AdS, and then computing correlators using AdS amplitudes. That's it.
Thank you very much. So we've already had some questions. Are there some more?
All the thing that you need is just every Cijk square to be 0 or product ofCijks to be 0, being positive.
So you just require that there are no imaginary OP coefficients.
No, imaginary.
That's it.
They can be real, but
Oh yeah, negative is fine.
negative is
The sign, yeah, there are definitely the OP
and product of
coefficients are
these could be
negatives.
negative as well.
No. Well, yes.
Product
Depends
of
on the
different-
situation you're considering, yeah.
Yeah.
If it's identical operators on the outside, then this can't happen. So this is a bit confusing. If we have some sort of IJ correlation function, that's what this would make sense.
Yes.
But yeah, more generally, the constraint is that the Cijks cannot be imaginary. But part of the reason the identical operator correlators are especially easy to work with is that when you expand in blocks, right, this is some structure constant squared, so it's obviously got to be positive. Now you have this game where you try to sum a bunch of positive stuff to make 0, and it's not possible, and then you learn something.
Any further questions?
Is there room for, is it still believed that this island constraint to point eventually, or that's ruled out?
No, I think that from what I understand, that is possible, in that we don't know a whole family of CFTs that live at different points inside the island. Right. Every time they revisit the problem, a lot of this is done numerically. I didn't say this. A lot of this is done numerically. They improve the numerics, the island shrinks. So the expectation, in some cases, is that with strong enough assumptions, it would shrink to a point. Right. So it might just be that no matter how well you are, no matter how good you are in numerics, if you run them with infinite precision, it still won't shrink to a point because you need to know a little bit more about the higher dimension operators in the theory. But yeah.
So I just want to ask what maybe if it makes sense to think about what the physical meaning of this crossing symmetry is about.
Yeah, so I think the analog with the algebras is a good one. So the associativity of the operator products is a useful notion. So if you think about a Lie algebra, then it has to satisfy the Jacobi identities, and this is like an operator version of that statement. So you have some operators that live in some theory, and you demand that their operator products are consistent with Jacobi identity, which tells you that when inserted in 4-point functions, you can form the OP however you like. So on some level, that's an answer to your question, but sort of from the broader CFT perspective on things, I think in some sense people are a little surprised at how powerful it's been. This idea is not new. It's over 30 years old, but it was sort of cast away as hard to implement and not totally clear, given the infinite set of data that characterizes the theory, how useful it could be to actually solve or constrain a theory. But it turns out that it's pretty powerful. So I think people are still sort of trying to understand how much can be extracted from this, but it seems like the answer is a lot.
Any further questions? If not, let's thank Derek again.